Hello everybody. I wanted to do a short video tutorial to explain how to install the software from this paper, analysis of thousands of EIS spectra. How to get it running on a computer, and how to use the basic commands, what they do, etc. So the first thing we will do is we will go to releases and go to the latest release, click on source code zip, and download the source code. And then we will extract the code in documents, and hopefully you can see that. If we go in the folder, we have a bunch of files, most of which are not being used at the moment. But for example, the user manual is here. And now that we have the source code, let's discuss how to get it running. The most simple way to get the source code running is to use a virtual environment for the Python programming language. So I'm going to assume from this video that you already have a virtual env on the machine. If this is the case on Windows, you can use the command mk virtual env, and then you would give the name of the virtual environment you would want to create. So this will create a new version of Python that you can install libraries on it, and it will not conflict with anything else on the system. It's an isolated environment. If I entered this, it would create a virtual env called demonstration and activate it, but I've already done that, as it takes some time. It's important to know that we need Python 3 for this. So if the default version of Python on your system is not Python 3, you would need to add as an option Python, for example, 3.6 or Python 3 when you create the virtual environment. Once you've created the virtual environment, let's say the next day you open your computer and you want to use the code, the first thing you have to say is work on, it's a command, and then you give the name of the virtual environment. For example, I call this one demonstration. And you will see that the prompt is now prefixed with the name of the virtual environment in parentheses. And then the next thing you have to do is you have to use the requirements from the website. So let me go back to the website. There you go. If you go here in the main code, you can see in the README instructions, so requirements, see requirements.txt, install the requirements by running the command line pip install something for the various things on there. So if we go to requirements.txt, this is in the source code, but you can also look at it online. You see the 4 things we must be sure to install, and we install them in the virtual environment itself. So if I do pip install Django equals 2.1.9, it will install Django 2.1.9, which is Django is a library that we use to keep track of the spectra once they've been fitted, and it's also a library for the future user interface. So if I were to do this for the first time, it would take some time, but I've already installed it on this particular virtual environment. So if you try to install something again, it will just say that it's already installed. The reason I've already done this is just because it takes a lot of time, or it took a lot of time when I tried it previous time. So at this point, let's say we also did the pip install matplotlib equals 3.0. Forgot to make the command line visible. So for example, if we do this, it will again say that we've already installed it. And then so matplotlib is the library we use for doing plots. And then if we install TensorFlow, which is the library used for the machine learning part, this is what we get. And normally, if you've installed the first 3 requirements, NumPy should already be installed with the right version. And in this case, it already is. So now that we've installed the requirements, it should be possible to run the code. And in order to run, yeah, this is visible. In order to run the code, I have a small, very small folder which contains a few examples of spectra. So I've pasted this folder here, and yeah. So then if we go back to the README to see what remains to be done, here's an example of a basic command. So there are a bunch of options. The first things are not very important. Python is just the language we use. Manage.py, EISMain it just means that there is this program that we're calling with this option, but this is the only option that we have to run the code. And then the mode in which we run the code is import process output, which means it reads in the spectra, applies the inverse model and then the optimization fine-tuning, and then outputs the results in an output file. And then log directory is the way we specify which pre-trained model we use. So for now there's only one pre-trained model, and it's called 1% training. And then there is another argument called input directory, input dir, and for this we will use the directory that we have copied to this folder, and then dataset, it can be anything. For example, demonstration 1, and then output directory could be anything again. For example, output demonstration 1. But in order to run this, right now if I run this, nothing will happen, because I am not in the right directory. So first I have to change the directory to be in documents, EISFitting, and then 0.1.1 is the version number. And then if I just paste this command again, this should do some fitting. Let's try it. So the messages that it prints are perhaps not the most useful for now, but it says when it's starting, when it's running the neural network, and when it's running the fine-tuning, and then it's just outputting the diagnostic information that you can just ignore for now. So when it says training complete, it means that the optimization is complete, and then it outputs the results to the file. So if we go to the Explorer, we can see that there's a new file called output demonstration 1, and it contains a bunch of stuff. So first let's look at the pictures that it contains. I think I need to add that window. So pictures, and oh, it doesn't show the pictures. How could I see the pictures? So right now I'm trying to show the pictures on the video, and it appears to not be working. Well, that's disappointing, but I guess I can leave that for now. Is there any other option? Can we see that picture? Yeah. Okay. So this is an example of the results. As you can see, there is the raw data. Then there is in blue the final fit, and in red is the fit that the inverse model produces. So the initial guesses can be just taken as a fit, but it's not going to be perfect. And then that's the red, and then the blue is when you've fully fitted. So that's an example of a different one of these fits. You can also, for the same plot, if you want to make your own figures, because we know that in academia you often want to make nice figures for a paper, for example. Then you would use can we see that? It appears that we cannot see that. This is unfortunate. Oh well. So, okay, how can I make this available? Basically, the CSV files contain different columns, which corresponds to the different types of data that's being plotted, and it has the raw data in it. For example, the original data frequency, original data real part of the impedance, imaginary part of the impedance, and then it has 3 columns for the inverse model and 3 columns for the fine-tuning, which allow you to reproduce the plots as shown here, or simply to make plots for a paper, for example. Alright, and then the circuit parameter fits is just an Excel sheet which has several columns again. One of them is the name of the file, which can help you find which spectrum you're looking at, and then you have all the parameters for the inverse model, all the parameters for the fine-tuning, so for the red curve and blue curve, and then you have the difference between the two. For now, this is a measure of uncertainty that we use. Okay, so you have to trust me that the data is what it is. You can try it and see for yourself. Perhaps it's worth looking at what's inside the import test. It contains various files, but for now the program just cares about the MPT files. And as you can see, you can have your own folders, and whichever organization works for you, it doesn't matter. It just looks at all the files in it. Okay, so then what is left is to look at the user manual. There you go. So if you want to do the fitting with the default options, you just run the program the way we've run it, but there are other options that you can use. And one of the choices you have is which circuit to use. So to help with that, I have made a user manual that has the option lists that you have to add. And then there's a longer, more explicit list of options that specifies everything, but there are some default values. So if you just specify the minimal options, it will do the same thing as if you specify the full list of options for a certain circuit. So let's say you want the circuit like it was in the original paper. You have to specify that there is an inductance and a Zark inductance. From the command line, again, let's look at the command line. From the command line, you would have a similar command, but let's say that, okay, you have the same input directory, same data set, but the output directory is going to be with inductance. And then you would add an option inductance and an option Zark inductance. And then if you run that, it will do the fitting, but with a different circuit. So the default circuit doesn't have the inductance, because sometimes there is no inductance in the system. But if you want to model inductance, you can. And this corresponds to the first circuit here. Here I am. Okay. And then the different options you can have is you can specify the number of electrochemical Zark components. So if you do specify it at 2, the default is 3. But if you say I just want 2, you will get this circuit. You just want 1, you will get that circuit, which just has 1 Zark element. And you can see the complete list of options. And then you can, if you look at the image, you can see you can remove the inductance by not specifying it, or by specifying no inductance. And you can also remove the Zark inductance, or remove both the Zark and the normal inductance. And then the newest option, which is a bit more interesting, is sometimes people want to put the diffusion element inside the Zark element. So if you want to go from this circuit where the diffusion element is in series with the rest of the circuit to that configuration where the diffusion, the Warburg element, is nested inside the first, namely the low frequency Zark component, you simply provide the option Warburg inception. And this allows you to do all the other options can still be provided, and the fits are often of a similar quality. And yeah, now let's just do a quick recap. So I have produced other fits that have inductance in them. I have used the same data set, which means that internally the same files are not duplicated. And if you have a large number of files, you will create a data set, it will import them, and then it will not look at the files anymore. It will just use the stored spectra. And yeah, you can use, maybe we can do another example where the Warburg is nested, Warburg inception, and change the output directory to inception, and then let it run. The neural network is relatively fast if you have a lot of files, but here you just have around 8 files, which means that you only see the initial cost of setting things up. It's not much slower if you have 1,000 files, for example, but the optimization fine-tuning can take a bit longer, but usually it is a reasonable time. For example, now it is done, and you can see that we have a new fit, and we can take a look at it. Image. For example, this is a circuit that has inductance, but it's not being expressed in the final fit, and then it also has the Warburg incepted or nested. Oh, and I just realized that this image was not visible, so there it is. So once again, if we look at the first circuit, we'll get this. if we look, so this doesn't have any inductance, and the Warburg is in series. Then with inductance, we get this. And if we use what I call inception, or just nesting of the Warburg, we get this. So hopefully this was helpful. Yeah. Thank you for listening.